For example number 2, we're looking at elevators. If you've ever been in an elevator, it probably has a little sign on it that says the maximum weight. So let's say we have an elevator. The weights of U.S. men are normally distributed with a mean of 194.7 and standard deviation of 32. So we want to know the probability that a random group of 10 men who enter an elevator will have a combined weight greater than the weight capacity of 2,000 pounds that's posted in an elevator. Okay, so this particular elevator can only handle 2,000 pounds. And so we're going to put 10 men inside, and we want to know what's the probability that they're going to be too heavy for the elevator. Hopefully it's small. Now, this problem is talking about combined, and we need to think about means because that's what the central limit theorem does. So if we have a combined weight of 2,000 pounds for the 10 men, that means we need each of their average weights. We need to take 2,000 divided by our 10 men. Okay. So what we really want to know is what's the probability that our average weight for these 10 men is 200 pounds. Because if the average weight for the 10 men is 200 pounds, they're going to exceed the weight limit. So that's where we're heading here. We're going to do this one just on the calculator, although you can do it by hand. Well, we'll do it both ways. There's a typo here. It should be normal CDF. Sorry about that. So first we'll do it by hand. So our average weight for men, I don't know, what was that, 194.7? And we want to know what's the probability that these 10 guys average over 200. Okay, so we're going to need our z-score. So that's x bar minus mu. And this is a sample. Remember, it's a group of 10 men, so we need sigma divided by root n. So we get x bar is 200 minus 194.7 over, what was our sigma? 32 over root 10. We've got 10 guys in this elevator. Backing up. I don't know if you caught this, but there's only 10. Now, normally we would say we can't use the central limit theorem here because our sample size isn't big enough, because it's supposed to be 30. But we can still use it because the population, where is it? The population is normally distributed. So even though our sample size isn't 30, like we sometimes like it to be, since the population weights are normally distributed, this is still going to be okay. Okay, back to calculating z. We plug this into our calculator and we get 0.5238. Now remember, on the table, if you're looking at values on the table, that only tells you the area to the left. So since you have area to the right, you need to do 1 minus the probability that z is less than or equal to 0.5238. So on the table, let's see, 0.6985. So our probability is 0.3015. Okay, so that's by hand. Using our calculator, we're going to use normal CDF. In case you forgot, the normal CDF is in the distribution menu. That's above variables, so it's towards the right side of your calculator. So our lower bound is 200. Our upper bound is infinity. Our mean is 194.7. And our standard deviation of our sample is the 32 divided by root 10. So we plug that all into the calculator, and the calculator tells us 0.3002, which you can see is slightly different than doing it by hand, but it's pretty close. So this is actually not terribly good. We have like a 30% chance that if you put 10 guys in this elevator, they are going to exceed the weight limit. So hopefully it's a small elevator that you can't actually put 10 guys in, because this is not a good situation. That probably is a little too high for my comfort, but whatever.